my god. Can't see myself in here. This video is not sponsored by Diet Coke. I just wanted some caffeine that wasn't coffee. Anyway, got another problem. So, let's say we have a game where we have some dice and we roll them, right? We got 6 of them for this particular game. Okay? Heck, I don't even know if you guys can see the dang board. Darn time of day. It's like 4 o'clock, thereabouts, so a little tricky to see. But I'm gonna push through with it anyway. In this game, we want to know 3 things. What is the probability of rolling a 1? What is the probability of at least 1, or rolling at least a 1, more specifically? C, what is the probability of rolling 2 ones? Exactly. Is that even readable? Yeah, kind of, sort of. If you guys can't read it, I'm sorry, but this is just going to have to do. Anyway, so in order to solve this particular problem, we just have to use our handy-dandy binomial distribution. And the way we do that is by, let's just set it up first, right? So our binomial distribution in Reif is given as this form here. We have w sub n of n1 is equal to n factorial, being the total number of objects that you have, n1 being the number of objects you want to know about, factorial, n minus n1 factorial. So the number you have minus the number of things you're interested in, times the probability p of one particular thing to the power of n1 objects, times the probability of q being the probability that it's not p, that's all q is, of n minus n1 objects. So in our case, we have, for part A, we have n is equal to 6, that's pretty much evident. n1 is equal to, well, 1, because we're only interested in one single ace. So we plug this into our distribution, and what we get is 6 factorial divided by 1 factorial, 6 minus 1 factorial, times the probability of rolling one of these guys is going to be 1 out of 6, exactly. So we have 1 to the power of 6, or 1 over 6, my bad, to the power of 1, times 5/6, 6 minus 1. So if we want to write this whole thing out, we have 1 times 2 times 3 times 4 times 5 times 6. 1 times 1 times 2 times 3 times 4 times 5. All these guys go away. We're left with 6. Power of 1/6. 5 over 6 to the power of 5. Right? We can throw that into a calculator, and we should get about 0.402. So you've got about a 40% chance of rolling exactly 1 ace, right? Or 1 snake eye, whatever the heck you want to call it, of rolling exactly 1/1. Okay. Part B, we want to know the probability of getting at least 1 of these. So the probability of getting at least 1 of these should be your total probability of rolling anything at all minus the probability of getting exactly 1. Because you know you're going to roll exactly 1 of them at a minimum anyway, right? So when we do that, we get that. So let's say that, let A be an event where we roll an ace. Right, so we just call that A. This is equal to 1 minus the probability of not having that particular event happen, times, or raise to the power of the number of dice that we have. So 6. Because what we're doing is that we're taking 6. We can think of this as either rolling these all simultaneously or just rolling them individually. So if we rolled them individually, then we'd have 1 roll, 2 roll, 3 roll, so on and so forth, till we have all 6 of our rolls. If we had 7 die, this would become 7. Right? Because the total probability sometimes is represented as a product of all of these things. So when we do the math, we get that this is equal to 1 minus 5/6 to the power of 6. You can throw that into a calculator. You're going to get that it's about 66.5% once you do the decimal conversion rate, right? Now, for the part C, we want to know exactly 2. We want to know what the probability is of rolling exactly 2. All that changes in our setup is that n sub 1 is going to end up equaling 2 instead of equaling 1 like we had in part A. So that changes up the math just a smidgen. So we would write for part C that the probability of rolling 2 is equal to n factorial. Just going to set it up again, just so that everybody sees where the dots are being connected. This is equal to 6 factorial, 2 factorial, 6 minus 2 factorial, probability, so that P becomes 1/6 twice, 5/6, 6 minus 2 times. So when we do that, you can throw this into a decimal. You can evaluate it just by, this is 4 factorial, this is 2 factorial. We can cancel out terms in the numerator and the denominator. And if you're feeling that bored, you can just multiply everything out and get your answer for 5/6 to the power of 4. But if you're in a hurry, this is going to be about 20.1% at the end of the day. So this problem's pretty plug and chug, and that's what I would expect to see, given that it's literally question 1.2 in the textbook. So that's how you would handle it.